we have described so far the last couple of weeks, we assume that the agent has perfect sensing, right? And actually, for example, the power law model ensures we can actually prove collision-free behavior in the absence of sensing error. The proof is a little bit more involved. I will upload the paper that has the proof. I don't want to talk about the proof because it's really involved. But if we were to, deploy the power law or the ORCA model or some other model on an actual robot, even a little bit of sensing noise is enough actually to lead to collisions, right? So, for example, for the power law, right? So, this is what we're getting with the power law right now, with no sensing error, meaning I have perfect sensing. I know the positions, the radii, and the velocities of my neighbors, and I can predict what they're doing, and I can react accordingly, right? So that's the behavior. Now, let's add a little bit of artificial noise to what I'm sensing, to what each agent is sensing. So this is what is going to happen. Eventually, we're going to start having collisions. So why is that? Well, at least in the power law, remember, we are estimating an energy based on time to collision, right? We have this energy term, right, which is based on time to collision. And we take the gradient of that energy to compute the force. A little bit of error in the sensed, for example, velocities or positions will change the formula, right, when we solve the quadratic, right? Because you have the quadratic equation, you put some values, so you put your own velocity, you put the sensed velocity of your neighbor, you put your own position and the sensed position, right? So if it's actually not true what you're putting there, it's not the correct one, the actual one, then you can end up with a collision, right? Now, we can actually extend the power law and ORCA and other models to account for uncertainty. The idea basically is to modify how we can compute time to collision before doing anything else. And then we can do things like I can compute the energy, for example, I can take the gradient, and so on, right? But if we do that, we get something like this, where now I account for uncertainty. And even though there is noise, I account for uncertainty, I account for that noise, so I'm able to plan safely, right? Okay, so let's try to formalize a little bit what I mean with uncertainty. So given an agent, A, there may be error in sensing another agent's radius, position, and velocity, right? And let's actually give me a second to highlight with R, X, and V. So let R denote the combined radius, the actual combined radius of agent A and agent B. Let X denote the actual relative displacement between agent A and agent B. And let V denote the actual relative velocity between agent A and agent B, right? And let now with hat denote the sensed one. What I do sense, not necessarily the actual one, but whatever I sense through my sensors, right? I make some estimate, for example, where my neighbor is, at which speed is moving, and how large the agent is, how big the agent is, right? So I'm going to denote these kind of values with a hat. And we're going to assume that the error is bound by some known constants. So basically, the difference between the sensed and the actual radius is less than a gamma. The difference between sensed and actual relative displacement is less than delta. and the difference between sensed and actual relative velocity is less than epsilon, right? And we can make the assumption these are actually known constants, in the sense that we can run experiments and figure out basically what is the error in my sensors, right? I can do that. Or for some robots, you already know that. Okay, so is it clear, like the formula here? What's going on? I sense a neighbor, radius, position, and velocity. There is some error between the actual and the sensed one. Basically, the sensed is the actual plus some error, right? Where the error, I know, this is a known error, right? I ran some experiments and I know the error, or the manufacturer of the robot already gave me that error, right? It tells me that, oh, if I use, for example, Kinect to sense something, or if I use that LiDAR to detect the distance between between nearby obstacles, there's that much of an error, right? So I know that. So let's look at the radius uncertainty. Accounting for such uncertainty is pretty straightforward. So, a collision exists if basically at some point in time, tau, the disks of the two agents, the distance between the center of the disks of two agents is less than their combined radius, right? So that's the formula that we see over here. That's a quadratic that you're actually solving, also for the first assignment, right? We know that the error is bounded by gamma. By combining these two inequalities, so by applying basically the triangle inequality, we're getting this. So effectively, by enlarging the combined radius by the error gamma, and then solving the quadratic, I can account for uncertainty in sensed radius, right? That's pretty straightforward. Nothing has changed. The only thing that changed is that when I solve the quadratic, instead of using the combined radius of the two agents, I'm going to add the error as well, right? And then business as usual. For example, if I'm doing power law, I'm going to take the gradient, right? I'm going to compute the force. Nothing has changed. What changed is that when I solve the quadratic, I just need to enlarge basically the disk, right? Okay, accounting for position uncertainty is also equally straightforward. And let's look at an example. So XA is the position of the agent who is doing the planning. XB with the hat over here is the position that we're sensing that our neighbor has, right? Basically, with uncertainty in position, the sensed neighbor can be anywhere in this gray area, because we assume there is some sort of an error, right? Delta away from my error is delta, right? So I can be here, I can be over here, I can be within a delta away from that, right? So we can simply consider basically the radius enlarged by delta and solve for, again, time to collision. Again, this is the same idea, right? I just enlarged the disk of my neighbor by the error, right? Why? Because, I know that the error between actual and sensed position is within a delta there's a delta error between sensed and actual one position, right? So the trajectories are going to collide under a larger combined radius, right? Does it make sense? It's straightforward, no tricks here, right? Nothing complicated going on. I simply have to basically inflate the sensed neighbor, either by gamma, if there's uncertainty on estimating the size of a neighbor, or by delta if there is also uncertainty in sensing the actual position of a neighbor, right? If not, so if delta is 0, if gamma is 0, I just use the actual values, right? Cool. Okay, let's focus on uncertainty in velocity, which is actually the most interesting case. So I mentioned that the error in sensed velocity is bounded by some constant epsilon, right? So v hat minus v is smaller than or equal to epsilon. What that means? That means that the true velocity of B lies in the disk centered at the sensed velocity and having radius epsilon. This is what it means. If by making assumptions where actually the true velocity lies inside that disk, where is actually the true velocity, right? Here. Different models of velocity uncertainty can be incorporated or accounted for. Right, there are different options here, right? The actual velocity could be any of those gray kind of like arrows that you see. And more, right? Anything in that disk, so to speak, can be the actual velocity, the true velocity, not the sensed one, right? So by making specific assumptions about where in that disk the true velocity lies, we can have different uncertainty models, velocity uncertainty models. So we're going to look at two of them. We're going to look at what I call isotropic model, where basically the error grows across all possible directions, meaning that we can choose any possible velocity in that disk. And so that's the isotropic model. And the other one, which I call adversarial, we're going to choose a velocity that actually promotes direct head-on collisions between the two agents. And let me start explaining the two models, and I hope things are going to become a little bit more clear. So let's go back to kind of like the examples that we were looking earlier on. Right, I have two agents, A and B, velocity at positions XA and XB over here. Let's translate everything into the velocity space. And let's also consider the local system centered at agent A, right? So basically, we're going to make agent A to be a point centered at 0 in the velocity space. And this is basically now have the inflated disk that accounts for the mass of both agent A and agent B, which is over here, right? In that local space, centered at XB minus XA, right? Okay, let's now look at the following example. Let me add the sensed relative velocity of the two agents. Right? This is what we sensed. In the velocity space, this is what we sensed as the relative velocity between the two agents. we mentioned that the true actual velocity can be any velocity inside that disk, right? Difference between the true and the actual is less than or equal to a constant epsilon, right? So the true velocity is any of those points inside that disk, right? So in the isotropic model, we are actually interested for the most threatening time to collision value, meaning we try to find the velocity inside the disk that leads to the earliest collision. Basically, what I'm saying here is that we have all of these possibilities, all of these dots inside that disk, right? So if I pick this velocity over here, which gives me this arrow, this vector over here, what is the time to collision value between that ray and this enlarged disk? Or if I pick this velocity over here, what is the time to collision between the ray that extends and the disk? Or if I pick this velocity over here, what is the time to collision between the ray and the enlarged disk, right? I'm looking at all these possibilities, and I need to keep the velocity that has the smallest time to collision, that will lead to the smallest time to collision value, right? So the most threatening one. So what I'm doing, I'm going to do actually multiple ray disk. I need to solve multiple ray disk intersection problems, right? That's one ray. I need to see when and if that ray is going to collide with my enlarged disk, right? Over here. There's another ray, there's another ray, another one over here, another one over there, and so on and so forth, right? If you think about this, basically, this becomes all of these kind of like vectors, all of these rays over here, actually lie inside this cone, right? Oop, that's not the cone I wanted to draw. Right? So basically, I need to solve a cone disk intersection problem. When the cone over here, this cone over here, right, is going to intersect with my large disk, right? Does make sense? Anyone? Either say yes or no, because I cannot see faces, so it's difficult for me.
Yes.
Yes.
Okay, thank you. If not, let me know, right? Don't be shy. So this is the cone, right? So we have a cone disk intersection problem, and we are interested in finding the very first time that the cone is going to hit the enlarged disk, right? What is a cone? It's a collection of disks, right? Actually, if I draw that byline over here, right? I extend it into infinity. So let's call this, since this is v hat, so this byline over here is v hat times tau, where tau is any value from 0 to infinity, right? So that's my byline. And centered at that byline, I have all of these disks, right? Well, this is not the disk, but you get the point. Right? The cone is a collection of disks, right?
Professor?
Yes.
This is in 2D space, so how
Yes.
it can be a cone? Shouldn't it be a triangle?
Sure, it's a triangle. Let's call it a triangle. That's fine. Yep. It's just kind of like I'm using a generic definition. Yes, it is. Because it's in 2D, it's going to be a triangle, right? Well, the problem with the triangle here is kind of like it's not closed, right? Yeah. You have an open triangle here. Let's put it like that. But I'm glad that, at least the point is clear, right?
Yeah.
You guys are following. Okay. It actually doesn't matter if it is a cone triangle because I want to simplify this. This is where I'm going with this. That's why I said it's a collection of disks, right? So there is that's why we're going step by step to basically solve this very quickly and very fast. So we have a collection basically of disks, right? That makes sense. And these are my disks, right? So what we want to see, what we are looking for is if these disks, any of these disks are going to intersect with the enlarged disk over here, and if so, which one is going to intersect first, right? So in general, any of these disks inside that open triangle, so to speak, let me write this as D denoted disk, right? Any disk inside the cone or the open triangle is going to be centered at V hat times tau, because it's going to be centered along that infinite line. And it's going to have a radius equals what? This is epsilon. It's going to have a radius epsilon times tau. So this basically denotes any possible disk inside that gray region. And what I want to find is that if there's an intersection between these disks and my enlarged disk, centered at minus x, having a radius r. That's the problem I want to solve. So how can I detect intersection between these two disks? I just check if the distance between the center of these disks is less than their combined radius, right? So basically, I can rewrite that problem, and this becomes plus, that's the problem, which is again a quadratic equation, right? It's very similar to what you guys have been doing before. And that's a formula here if you want to see it in a much nicer format. And I can solve this using, again, one of the formulas that we saw before and we talked about for homework 1. And here's the actual solution. Right? It's a quadratic equation. Again, there are two possible solutions, but because of the problem, actually, we only care about only one, right? The smallest positive root, right? If such root exists, positive, that's the solution. And if I go back to what you're using for the homework, this is what you're using for the homework. This is the solution if we account for velocity uncertainty with that isotropic model. The only thing that has changed is that in the coefficients A and B, these two terms appear. That's the only difference. Like if you have like a generic time to collision formula, that's the only change you have to do. You basically have to change the A and B coefficient, such as you incorporate this epsilon over here, where epsilon is the error between true and sensed velocity. And given that, then basically we can compute the interaction energy, having solved for that, right? So we found this time to collision value, which I call isotropic time to collision, just to differentiate from standard time to collision, so to speak. It's just a name, guys, not really, but everything else is the same. So for example, I define my interaction energy as before. It's a power law relationship with respect to time to collision. Again, I'm going to take the negative of the gradient of that energy. And I'm going to get the force, which is of the same type as the standard power law model. What actually has changed is basically these things over here. Let me get rid of my notes over here. There we go. So the only thing that has changed from the standard formula is the following. A, whenever we see this time to collision value, now this time to collision value accounts for this isotropic error, right? So it needs to be computed using this formula over here, right? And of course, since the discriminant also appears in the force, again, the discriminant basically uses those A and B coefficients, so those coefficients will have that epsilon value as well. Does it make sense? Like, there's nothing tricky if you go and see, if you have to code that, and that's actually the homework. If you have to program the standard power law and the isotropic version of that, the only difference is that when you compute the time to collision, A and B has this kind of coefficient epsilon over here, right? Where if epsilon is 0, everything is the same, right? You get the standard formula. The force, the nature of the force, so to speak, is the same. But now you're able to account for velocity uncertainty, right? Okay, so in the isotropic model that we've seen right now, we considered all possible velocities inside a disk, and then try to detect the most threatening one, right? The one that is going to lead basically to the minimal time to collision between that velocity in our enlarged disk, right? So this is what we did. Now, in the adversarial model, we're going to make a specific assumption about where the true velocity lies inside that disk over here. In particular, we're going to assume that the true velocity leads the two agents towards a head-on collision. That's the name, that's why we use the name adversarial. In other words, the vector that is going to point from the sensed velocity v hat to the true velocity v is going to point towards the disk centered at xb minus xa, meaning it's going to point towards that disk over here. And this is the vector. And this is the corresponding true velocity. So basically, the adversarial model considers the behavior of the isotropic model at the limit as the agents approach towards a collision. It is, you can think of this as a subset of the isotropic model, where I'm making the assumption that the true velocity follows that relationship over here. What I did kind of like to make it a little bit more clear what I did here. That's the vector that points towards my large disk, right? If I add that vector over here, let me go back. That was the vector. If I add that vector to v hat and I scale it down, this is what I'm getting. And that's tip of that vector is basically my new velocity, right? And now we have a rate disk intersection problem. We basically have, remember that's the formula that we usually use to solve for time to collision. Now, if I replace V with a new formula, I'm going to get this equation over here. Similar to isotropic, I can solve this using the quadratic formula, compute then the force, take the gradient of the force, by taking the gradient of the force, of the energy, sorry. The problem with this is that actually the derivative, or the gradient actually, is much more involved. If you try to, expand this and then figure out what the solution of the time to collision, and then plug that solution to the energy function and take the gradient of that energy function, the final form that you're going to get is really ugly, much more involved to make this implementation work easily. So a simple alternative solution is the following. Just use the standard power law, do everything as you do with the standard power law, meaning you have this, you compute time to collision by solving that, you compute the force basically using the formula that you have in the standard power law. But every time actually we see in our formulas V, every time we see V, right, we're going to replace V by that value. So I'm just going to substitute V with this value over here. And the results are more or less the same if actually I'm trying to do the more involved approach, where here initially I incorporate V, not numerically, but just like the math, right? The formula of V here. Then I have to expand, solve, new equation for time to collision. Then I take the energy. From the energy, I take the gradient of the energy with respect to position, and this eventually is going to give me a force. If I do all of this, the final force is going to be much, much more different than what you see here, and much actually uglier and difficult to program and compute actually the gradients and so on. Because of that, what we're doing here, we don't do that. We actually work as we usually do, but when we have to substitute some values, for example, when I go into the, in a second, here, when I go to, well, that's the wrong thing, here. When I go here and I solve for time to collision, the solution does not change, but whenever I see V, I'm going to replace V by V hat minus this. it kind of like to close the loop with the example that we saw before. So here are the two sensed agents. So here's my actual agent, here's the sensed agent. I have uncertainty velocity. The isotropic model will consider all possible velocities around the sensed one. Basically, the error grows across all possible directions. That means that the neighbor, so agent B, can eventually be in any of those kind of like disks that you see over here, which they, again, if I draw this thing, this is my open triangle, right? The earliest collision time among all of these possible disks gives the time to collision, right? And that's the isotropic model. Now, with the adversarial, we assume that the true velocity leads the two agents towards a head-on collision. So that's the only disk I'm considering to compute time to collision. And we can, experimentally test both the effectiveness of both models for avoiding collisions in the presence of noise. So here what we see on the left, that's the setup experimental scenario, number of agents in a circle, similar to the one that you guys have for homework 1. But now, we start going to add noise to the sensed velocity of our neighbors. And here we're going to make the assumption, or we assume, that the error is 0.2. So the error between sensed and true velocity is 0.2. As you can see in the graph over here, as long as the noise is less than my error, both with the adversarial and the isotropic model, there are no collisions. With the standard power law, of course, we already start getting collisions because we cannot account for uncertainty, right? Also note that we can actually make theoretical guarantees for collision-free motion for the isotropic model, not for the adversarial, but for the isotropic. Kind of like behavior-wise, if this thing wants to switch slides. Let's see why this can happen. Behavior-wise, these are two models. On the left is the isotropic. On the right is the adversarial. Now, because the agents will move in general more conservatively compared to the standard power law model because they give more space to each other due to the uncertainty that they have in the motion of their neighbors, right? So it might take longer for them to reach their goals. So kind of like we use this 4-way crossing scenario along with other scenarios like the 3-agent and the 8-agent scenario that you guys have for the homework, and a hallway scenario. And more or less what we saw is that the travel time gets, when we account for uncertainty, the travel time gets slightly longer just by a small amount. Not too much as compared to the original power law model. Even in the crossing scenario that we just saw, this 4-way crossing, the travel time between the original power law over here and the isotropic over here increases roughly by 8% only. Also, note that typically the adversarial model is much more time efficient compared to the isotropic. And the reason is, again, the isotropic considers all possible directions where the error can grow. That means that eventually the agent or the robot ends up being much more conservative, right? Has less space, so to speak, to maneuver, or tries to give itself more buffer. That's actually a more accurate description here. It tries to give itself more buffer, right? Because it accounts for error in all possible directions, right? And because of that, exhibits behavior much more conservative as compared to the adversarial, where we are only making assumption that what actually the true velocity is basically a velocity that leads us towards a head-on collision. And this is an example implementation of real robots. What you see here is the isotropic model. I don't think you need to. Right, they are able to avoid collisions, accounting for uncertainty, and all three of them moved rather than one of them had to wait for the other two before it reacts. A couple of more things and then we'll get the break, just to close the gap, and then you have questions after the break. It's a very simple extension to the parallel model, leads to relatively good motion. We can actually provide theoretical collision-free guarantees for the isotropic model. Can be applied, as you saw, to differential drive robots, and we're going to talk about this next, in general, how we can implement things on some mobile robots. Similar models to account for uncertainty exist for velocity obstacle collision avoidance models such as ORCA. Again, the same kind of like idea here. Everything is time to collision based. We try to account directions where the area of velocity can grow, and after that, we construct half planes in with ORCA at least, and we look at the intersection of those half planes. Oh yeah, one final thing, and I'll stop here. That's the second assignment. Probably too tiny, but let me kind of like summarize what's going on. What I'm going to ask you to use the same scenario that you are using for homework 1, but this time you're actually going to implement the parallel model. So initially you're going to implement the parallel model. You're going to see hopefully much better behavior compared to what you had in the first homework. And as soon as you have the standard vanilla parallel model implemented, then you're gonna actually incorporate also uncertainty. Meaning that you actually gonna make the assumption, you're actually gonna implement the isotropic extension. You're gonna make the assumption that there is some uncertainty in the velocities that you're sensing of your neighbors. That velocity extends across all possible directions. So you're going to do the isotropic model, you're going to implement the isotropic model, which means what? I'll go back to this. That means that it's a very minor change in what hopefully you already have implemented, the vanilla parallel model. Basically, you just need to add those terms in your time to collision formula, right? While you're computing things. And of course, if epsilon equals 0, then you're going to get the vanilla parallel model, right? So it's literally just one implementation. Nothing changes. It's just that if you have a time to collision function, hopefully, I assume you do, you're going to have another extra parameter here called epsilon or whatever you want to call it that denotes the error between sensed and true velocity, right? And your function is going to return time to collision. And when you have time to collision, you can compute things using that formula. Note that in the formula, the discriminant appears, of the quadratic appears also in the formula of the force. So you should compute that as well, right? Maybe make the time to collision function to return also the discriminant, right? Or the square root of the discriminant. Cool. Let's take a break. Resume at 5:30. Then feel free to ask how many questions you have in your minds, and we'll go from there. Cool. See you guys in 15 minutes.
So it was better, but then I ran it with the weight 0 switching, so I was like, yeah. So I did. How makes sense? Is this really a uniform sample?
I think it's a focus thing. Between,
Yes.
yeah, so it was on this one. This one was back here.
But that's not trying to fix it.
Oh, there it is. Okay. So we can kind of see this a little.
That is like just a random from 0 to
Oh, it's the Zoom thing.
okay.
It's always going to take ideally it's supposed to check the velocity.
I mean, that's an easy way to test that. Just export this if you want to and visualize it in Excel.
See any other?
But you can export those values once.
There's no other set.
Like, you know, they've done like
1 and 0.
to fill them out here, copy paste them into an Excel file.
Yeah, I guess that's it. Unless here this one makes it worse.
If not, maybe. I mean, this looks correct to me. I may have to do but yeah, that's the trick here.
Have you tried this, the preset one?
Do that. Otherwise, I mean, whatever you're doing is not wrong. It's not here from sampling. Then I end up promoting more samples in the edges of the, so to speak, rays of the disk, rather than uniformly across the entire.
I didn't think about the fact that you had to compare it together. It has
Yeah.
to have a greater density.
Yeah.
Yeah, that's what
That's
I
the
did.
trick here.
I had to Google that for a while.
Yeah, I think like we're going to talk about this problem on Wednesday.
I think it's
That's
down.
actually a common question if you, I mean, I know you have
That's
a problem.
blurry too. Try it.
That's a common question if you are interviewing.
Oh, that's pretty clear.
My weight,
Well,
and it's still doing it.
Can you go to yeah, I have to make some idea.
I added collision.
what happened? Maybe we can use that, but we should just turn around and talk to him.
Yeah, to make it, yeah. But this conceptually you right?
Like you said, maybe it's the camera.
Those are your
Mhm.
So that's still the problem. Like the neighbors not be here, the neighbors be after that.
Yeah, if we go back to this.
You have two loops, right? The first loop is gonna be
Just drive it around. Oh, it sort of moves it.
for each constant velocity. That's the outer loop.
That's what you try
It's
to.
constant velocity.
Won't that make it look at neighbors that are 40?
Oh, you move the signal.
But you need to evaluate. Let me say this and then maybe
Yeah, just
for every constant velocity, you can do two things. One,
So, you know,
that the distance
this
between the constant velocity and the
I
velocity.
don't see any other settings here. Do you-
Right. Two, compute this scaling constant K or whatever weight and minimum time to collision. That means that you need to go for every neighbor. Right? Time to collision between the candidate velocity, position of the agent,
This is just gonna
Yeah.
velocity,
Or maybe this one, but we.
and the neighbor.
Oh, but, oh, right, because we could turn it and just be behind us.
So that's another look inside that.
Why did you move to other one?
So,
I see what I'm missing now.
Oh, move this.
So,
like this.
to compute that,
Wait,
let's start with this,
Yeah, I guess this one, then we should turn around. Except
yeah.
those guys are.
Yes, better.
Let's call it house. I know that, yeah,
That's not cool.
right?
All it goes, yeah.
How
Yeah, he's still cut off.
less than
Yeah.
PC. That's your main one.
That camera is weird.
But you have to run this over all neighbors, right?
As long as
Eventually, you
Yeah.
have
that's what he said.
a minimum PC.
I don't think it's
Which
Unless
you
they're
got here.
direct
You got
control.
one and two
It
together,
seems like
and that's your
the
house,
focus is off or something.
Yeah.
right? Does it make sense? I mean, you have to do two things, right? It's a cost function. That's the second term or the first whatever, that's the average. Right?
Yeah.
I'm just trying to, that's a different problem, right? But I'm not just saying. For that term, you need to go through its name and compute this, right? As soon as you have this, you can compute the cost. And again, you have some variable that